Continuing on physical chemistry, chapter 15. We're in section 4 now. And in the last section we talked about average molecular speed. Now we're going to talk about what is the distribution of this molecular speed. Now let's say we have a spherical shell here. So this is in velocity space again. So we have this shell within a shell. The inner radius is the velocity. This outer radius is the velocity plus the change in the velocity. So we're going to talk about what is the number of atoms within this shell here. So this dV, this is the shell layer, the thickness of that shell layer. So we're going to have the velocity plus the differential of velocity. Now, question that Maxwell Plank asked: how many molecules do we have that have a speed that are within this range of whatever speed plus the change in speed? So we're going to call this speed the differential of the number of molecules of that speed. So dV, remember, is infinitesimal. So it's an infinitesimal interval of speed. And likewise, so this differential of the number of molecules at that speed, that's the answer to Maxwell's question. And then of course, capital N would be the total number of molecules. So we have the fraction of the molecules that are traveling with speed between v and v plus dv is going to be the differential of the number of molecules at speed v divided by the total number of n, which is proportional to dv, differential of the speed. So the differential of the speed, it also depends on v though. So what we need is a function that relates all this so that we can have an equality sign instead of just a proportion or whatever. So we're going to have this differential of the number of molecules at speed v divided by the number of molecules is going to be this function capital G of v. So times the differential of speed. So this g of v, this g is a function. We don't know what the function is yet, but hopefully we can figure it out. So g of v, it takes into account both the speed and whatever interval we're talking about. And likewise, g of v is a distribution function for molecular speed. So this is a probability density function for the speed, molecular speed. So that means this ratio, the differential, the number of molecules at speed v divided by n, is the probability that any molecule is in that shell, the range of v to v plus dv. So let's talk more about this distribution of molecular speeds. So we have a v1 and a v2. Let's say we have equally spaced intervals from v1 to v2, and each one is dv. So the width of each infinitesimal, so they're infinitely thin, remember. The width of each of these is dv. Now we're going to say capital P, so lowercase r is probability. That's not the way they do it in math, but we already used, P for pressure and so on. So we need something we can recognize. So we want the probability that the speed of our molecule is between or equal to speed 1 and speed 2. Now this is a closed interval. So we have the probability that the speed is between v1, oh, that should be v2. Whoops. Hang on. Let me write a 2 here so I don't forget. There's a 2. Anyway. So that's going to be equal to this function g of 1 dv plus g of v1 plus dv plus g of v1 plus 2 dv plus etc. all the way to g of v2 dv. So it's summing up all the parts. That's an infinite sum of infinitesimal values, which of course, hopefully if you're watching this, you know that's a definite integral. So the probability that the speed of our molecule is greater than or equal to v1 but less than or equal to v2 is just going to be the integral from v1 to v2 of this function g of v dv, and that's going to be equal to this differential number of molecules at speed divided by n. But we still haven't figured out what is this function g of v. Well, it was 1860 that Maxwell Plank was able to figure this out. Now, the one thing he knew that the integral from all the way to 0 to infinity of this function with respect to speed has to be equal to 1. If you're taking probability, that's because you know the sum of all probabilities, everything that's possible, has to equal to 1. That's the definition of a probability distribution function. So, derivation g of v. So this is a key function in kinetic molecular theory. To do this, he started out with a couple assumptions. Okay, so the first assumption is that the velocity distribution is independent of direction. It doesn't matter if you're going x, y, z, up, down, left, right, whatever. So he's saying all directions in space are equivalent. Now, of course, we're going to ignore gravity, which actually doesn't make that much difference anyway. At the room temperature, gravity is actually pretty weak. It doesn't make that much difference. And of course, this is only going to be true if we have no external forces. If you had a strong electric field or a magnetic field, well, then that's going to be another problem you're going to have to deal with. Now, the second assumption is that the values of the y component of speed and the z component of speed do not affect the probability associated with the x component of speed. So again, this is kind of almost saying the first one is that x does not affect y and y does not affect z, etc. They're independent dimensions. So let's talk about this distribution function for the x component of speed or velocity. The x component of velocity. So we're going to use lowercase g for this function. So we're going to have g of the x component of velocity. It's going to be the distribution of the x component of velocity. So that the ratio, the differential of the number of molecules with that x component of velocity divided by the total number of molecules is going to be equal to this function of g of the x component of velocity times the differential of the x component of velocity, where the differential of the x component of velocity, or the number of molecules with the x component of velocity, is the number of molecules having their x component of velocity lying in between vx and vx plus dvx. So again, we're talking about infinitesimals here. We're going to be doing calculus. So that gives us, the differential of the number of molecules of the x component divided by the total number of molecules. That's going to be equal to this lowercase g function, x component of velocity times the differential of the x component of velocity. Now remember, n is the total number of molecules that are traveling, which is all of them, of course. And again, remember, it's a probability distribution function. So the definite integral from minus infinity to infinity, remember velocity can be negative, of this function g, x component of x, times the differential, or with respect to the x component of velocity, it's going to be equal to 1. And again, like I said, x component, it can be either positive or negative. And again, we're just assuming it's symmetric, therefore everything that we say of x is also going to be true for y and z. Therefore, we also have the definite integral from minus infinity to infinity of g of x component of, or y component of velocity with respect to the y component of velocity. That has to equal to 1. And the definite integral from negative infinity to positive infinity of this g function of the z component of velocity with respect to the z component of velocity. That too has to equal 1. So here's the question still. What is the probability that a molecule will simultaneously have its x component of velocity in the range of vx plus dvx and its y component of velocity in the range of vy to vy plus dvy and its z component of velocity in the range of vz to vz plus dvz? Well, by assumption number 2, we're going to say that their probabilities are independent for various x component velocity values versus y component and z component. Now, to make sure you understand what that means, we're going to talk about a standard deck of cards, remember. Let's say that we have a probability of a heart. Well, there's 13 ways to do that out of 52 cards, so the probability is 1 in 4. Now, the probability of getting a queen, there's 4 queens, 52 cards, so the probability of that is 1 in 13. So, since these are completely independent, what is the probability that you get a queen of hearts? You just multiply those two. You get the probability of a heart times the probability of a queen. You get 1/4 times 1/13, and you get 1/52. So the answer to our previous question is going to be just to multiply that. You're going to get this g of the x component of velocity times the g of the y component of velocity times the g function of the z component of velocity times the differential of the x component of velocity times the differential of the y component of velocity times the differential of the z component of velocity. Since these are completely independent of each other, we can simply multiply them. Now remember, capital G of v is the distribution function for speed. This multiplication we just did, that's the distribution function for velocities. Remember, velocity is a vector, speed is a scalar. We're talking about two different things. Of course, they're going to be related, and we'll see how later. So equation 1, we're going to say the speed squared is going to be the x component of the speed squared plus the y component of the speed squared plus the z component of the speed squared. And then equation 2, we're going to say this g function of the x component of velocity times the g function of the y component of velocity times the g function of the z component of velocity. We're going to call that phi of the velocity, or phi. So phi of v, that's a lowercase v for speed. So remember, this phi of v is not the same as our g function yet. So we're going to take this equation 2, we're going to take the derivative of the equation 2 with respect to vx. So we're going to hold the y component and the z component constant. So we're going to have the partial derivative with respect to the x component of x of this whole function, g of v of x times g of v of y times g of v of z. Oops. And that's going to equal to the partial derivative with respect to x holding y and z of phi of the velocity. So remember, g prime of v of x is going to be the derivative of g of v of x. We're going to have to use the chain rule. So we have the partial derivative with respect to the x component holding y and z constant of phi of v. That's going to be the differential, or the derivative of phi of v with respect to v times the differential of v with respect to x. So equation 3, we're going to have g prime v of x times g of x of v of y times g of v of z, and that's going to equal to the derivative of phi of v with respect to v times the partial derivative of v with respect to the x component. Now we want to substitute this term, this partial derivative of v with respect to the x component of v term. So we're going to take the differential of equation 2. So we're going to get 2 times the velocity dv, and that's equal to 2 times the velocity x component of velocity dvx plus 2 times the y component of velocity times the differential of vy plus 2 times the z component of velocity times the differential of velocity. Obviously all those 2's cancel out, so we just get v dv is equal to vx dvx plus vy dvy plus vz dvz. Now we're going to say we're going to hold y and z constant, so their differential is going to be equal to 0. So those terms drop out. So we end up with just velocity times the differential of velocity is going to be the x component of the velocity times the differential of the x component of the velocity. Doing a little algebra, we get the x component of velocity divided by the velocity is going to equal to the partial derivative of the velocity with respect to the x component of the velocity. So now we can go back and substitute that into equation 3. So now we have equation 4. We have g prime of the x component of velocity times g of y component of velocity times g of z component of velocity, and that's equal to phi prime of velocity times the x component of velocity divided by the velocity. So now we can multiply equation 2 by Vx. We'll call this equation 5. So we get Vx times g of Vx times g of Vy times g of Vz, and that's equal to Vx times phi of V. Now we're going to divide equation 4 by equation 5. Hopefully that means equation 5 is not equal to 0. So equation 6, we get g prime v of x divided by vx g of vx is equal to 1 over v times phi prime of v divided by phi of v. And likewise equation 7, same for y. We'll have g prime of the y component of velocity divided by the y component of velocity times g of the y component of velocity, and that's equal to 1 over v times phi prime of v divided by phi of v. And then equation 8 is going to g prime of z component of v divided by the z component of v times the g function of z component of velocity. And that's going to be equal to 1 over the velocity times phi prime of the velocity divided by phi of the velocity. Then equation 9 here, we're saying they're all equal to each other, right? So we're going to say that g prime of v of x over v of x over times g of the vx is going to be equal to g prime of v of y over vy times g of vy. And that's equal to g prime of v of z divided by vz over g of v of z. So we're just going to define that as b. Now, here's something interesting to think about. Those three terms are equal, but they're independent. Therefore, they must be constant. So b is a constant that is independent of the x component of velocity and the y component of velocity and the z component of the velocity. So we have b times the x component of velocity is equal to g prime of v of x divided by g of v of x. Then just rewriting that a bit, we get the derivative of g with respect to vx divided by g. That's going to be equal to dg divided by g times dv of x. Now we're going to separate the variables. So we're going to have dg over g, and that's going to be equal to b times vx dx. Now we can integrate that. So we're going to have the integral of dg over g, and that's going to be equal to the integral of b times vx dvx. Now let's say that the natural log of g is going to be equal to b times 1/2 x component of velocity squared plus c. So the integral of 1 over g is natural log of g, and so on. So that's our integral. But even though it's a definite integral, we're going to have an integration constant. Technically, we'd have an integration constant on both sides if we combine them. So we have one integration constant. So we could take e to both sides. So we get g is equal to e to this power, 1/2 b vx squared, and then times e to the c. Now again, just to simplify the math, we're going to define another constant and just say, okay, a is the natural number e to the c power. So now we're just going to pull that in front and say, okay, g is equal to whatever constant a times this e, natural number e, to this power, 1/2 times this number, or constant b, times the x component of the velocity squared. So we actually have our function now, except that we need values for a and b to make it useful. So we have this function g of v of x times g of v of y times g of v of z. That's equal to phi of v. So we get phi of v is equal to this constant a times e to the 1/2 b x component of velocity squared, and then times a times e to the 1/2 times the y component of velocity squared, times a times e to the 1/2 b vz squared. Combining terms, what we've got here, is that this phi of v function is equal to a cubed times this natural number e to the power of 1/2 times b times, you add the exponents. So you get v of x squared, x component of velocity squared, plus y component of velocity squared, plus the z component of the velocity squared. So you get v squared is equal, remember that v squared, using the Pythagorean theorem, is the x component of velocity squared plus the y component of velocity squared plus the z component of v velocity squared. So we say that phi of v is equal to a cubed times e times 1/2 times this other constant b times the velocity squared. So we're going to use this integral again from minus infinity to infinity of this g function x component of velocity with respect to the x component of velocity is equal to 1. And we're going to use that to see what are the values of a and b. So we have this a times the integral from minus infinity to infinity of e to the 1/2 b vx squared dvx is equal to 1. Now, b is actually going to have to be negative. Otherwise, this integral would not be finite. If b was equal to 0, this wouldn't make sense. And of course, if b was greater than 0, it wouldn't integrate. It would be infinite. So, because b is less than 0, this shape is actually a bell curve. So we're going to use the table of integrals to evaluate. And what we have here is that the integral from minus infinity to infinity of x to the 2n times e to the minus ax squared dx is equal to 2 times the integral from 0 to infinity of x to the 2n times e to the minus ax squared dx. Now, a is, in this case, has to be greater than 0. It can be an integer, 0, 1, 2, 3, etc. So we can also use n is equal to 0. So actually, that's what we're going to do. So we're going to get vx squared is going to be equal to x squared. It's just a dummy variable. So the dvx is going to be equal to dx minus a equals 1/2 b. Oh no, wait, dvx is equal to dx. And then the minus a is equal to 1/2 b. So we're just converting variables here from what we had before to match the integration table. So we got this definite integral from 0 to infinity of e to the minus ax squared dx. And the answer is pi to the 1/2 power over 2a to the 1/2 power. So a is equal to minus b over 2. So we end up with 2 times a times the definite integral from 0 to infinity of e to the 1/2 bx squared dx, or dvx. And that's equal to 2 times a times this whole big quantity, square root of pi, over 2 minus negative b over 2. That's the square root 2, 1/2 power. And that's equal to 1. So what we get is that a is equal to minus b, the square root of minus b over 2 pi. Now, g of v of x is equal to minus b over 2 pi to the 1/2 power times e to 1/2 vx squared. So we got rid of one variable, we got rid of capital A, but the question is, what is this lowercase b? Now we know that the average speed squared is equal to 3 times the x component, average x component to the velocity squared. So we also know that the average energy of translation for a molecule is equal to 3/2 times k times t. And remember, lowercase k is the Boltzmann constant. So we have the average energy of translation, that's 1/2 m times the average speed squared, or v, speed squared. So using substitution, we get 3/2 kt is equal to 3/2 m times the average speed squared. Now we have equation 10. Equation 10 says the average x component of speed squared is equal to k times t over m. Now let's say we have w as some continuous variable, such as speed. So then the function g of w is going to be the distribution function for w. What that means is that gw times differential w is the probability that w lies between w and w plus w. We've kind of talked about that before when we talk about that sphere, velocity sphere. So we have the average value for this function of w is going to be equal to the definite integral from the minimum value we're interested in to the maximum value we're interested in of this function of w times g of w with respect to w. So there's see the handout figure 45 to see why that's true. So we have the average speed, or the average of f1 plus f2, and that's equal to the average of f1 plus the average of f2. So that's adding. But you can't multiply. You can't say the average of f1 times the average of f2 is not equal to the average of f1 times the average of f2. We also can say, though, that if you have an average of c times f of w, you'll still end up with the c times the average of f of w. So these are just some rules for mathematics, figuring out this probability distribution function. So, let's see, where were we? So the average velocity of x squared is what? Well, vx is w, so f of w is vx squared. Our w min is going to be minus infinity, and our w max is going to be positive infinity. Then we have v of x squared is going to be the average x component of velocity squared is going to be equal to the definite integral from minus infinity to infinity of the average of the x component of velocity squared times this g function of v of x dv of x. So we're going to substitute in g of v of x and use the table of integrals to find out what that is. So we have the average x component of velocity squared is going to be equal to the minus infinity to infinity of v of x squared times this quantity minus b over 2 pi to the 1/2 times e to the 1/2 b vx squared dvx. So now we have the average v of x squared is equal to minus 2 times the square root of minus b over 2 pi times the integral from 0 to infinity of x squared times e to the 1/2 bx squared dx. So we get the integral from 0 to infinity of x to the 2n times e to the minus x squared dx. That's equal to 2n factorial times the square root of pi over 2 to the 2n plus 1 times n factorial times a to the n plus 1/2. Now n is equal to 1, therefore we have x squared. We have x squared, therefore n is equal to 1. So we have the integral from 0 to infinity of x squared of e to the minus ax squared dx, and that's equal to 2 factorial times the square root of pi times 2 to the 3rd power over a to the 3/2. Now we have the average x component of velocity squared is equal to 2 times minus b over 2 pi to the 1/2 times the integral from 0 to infinity of x squared times e to the bx squared over 2 dx. So substituting that integral, we get 2 times minus b over 2 pi to the 1/2 times 2 factorial times pi to the 1/2 over 2 cubed times minus b over 2 to the 3/2. So doing a little arithmetic, that's 2 times minus b over 2 to the 1/2 times 2 times pi to the 1/2 over 8 pi to the 1/2 times minus b over 2 to the 3/2. All that simplifies to just minus 1 over b. So we get the average x component of velocity squared is just equal to minus 1 over b, and average vx squared is equal to kt over m. So minus 1 over b is equal to kt over m. So b is equal to minus m over kt. Now remember, m is the mass of one molecule, k is Boltzmann's constant, and capital T is temperature. So we have g of v of x is equal to 1 over n times the differential n of vx over dvx, and that's equal to m over 2 pi kt to the 1/2 power times e to the minus mvx squared over 2 kt. So at constant temperature, the m over 2 pi kt 1/2 term is constant. Now we know the k is equal to 1.38 times 10 to the negative 28 joules per Kelvin. So that means kt has units of energy. Kt is what we call a characteristic energy of the system. Now remember, we said before the directions are independent, so g of v of y is equal to g of v of x is equal to g of v of z. Now the integral from negative infinity to infinity of g of v of x dv of x is equal to 1. So now we have the whole function of all three. Capital G of v of dv is proportional to g of v of x, gv of y, gv of z, dv of x, dvy, and dvz. Now remember, we have this sphere here again. It's got a radius v, or v plus dv. So this hollow shell, this is what we're interested in. This dvy, dvz, dvxyz, that's the volume element in velocity space. This is a sphere within a sphere. And any cube, it's going to have dimensions of dvx times dvy times dvz. Now we want to take the sum of the shaded volume, all those little cubes around the sphere. Now remember, the volume of the larger sphere, that's just 4/3 pi times v plus dv cubed. And the volume of the smaller sphere is just 4/3 pi v cubed. So the shaded volume is going to be the difference between those two. 4/3 pi times v plus dv cubed minus 4/3 pi v cubed. Now distributing all that out, then we have 4/3 pi times v cubed plus 3 v squared dv plus 3v dv squared plus dv cubed minus 4/3 pi v cubed. Now these two cancel out, so we're going to get 4/3 pi times 3 v squared dv plus 4/3 pi 3 dv squared plus 4/3 pi dv cubed. Now these terms, dv squared and dv cubed, are going to be really small. So we're going to ignore them and just look at the first term right here. So we're going to end up 4 pi v squared dv. And that's going to be equal to the volume element that we're interested in. So we have g of v dv is going to be equal to the sum over this whole shell of m over 2 pi kt to the 3/2 power times e to the minus m times x component of velocity squared plus the y component of velocity squared plus the z component of velocity squared over 2 pi or 2 kt with respect to the x component of velocity, the y component of velocity, and the z component of velocity. So that gives us g of v of dv is equal to m over 2 pi kt to the 3/2 power times e to the minus mv squared over 2 pi or 2 kt times 4 pi v squared dv. See how we substituted that in here. So g of v of x is the distribution of velocity. Capital G of v is the distribution of speed. So g of v of x is going to be equal to this a times e to the minus avx squared. Now this is what we call a Gaussian function. And notice it's symmetrical about the Notice it's symmetrical about the y-axis, even if I didn't necessarily draw it very well. I said A, but it actually says X here. Well, yeah, here's your y-axis. But anyway, so we're just assuming that the temperature is about 300 Kelvin, or room temperature here. So, or not, here we go. So the temperature 300 Kelvin, or yeah, the temperature changes. When the temperature increases, the velocity increases. So anyway, so here's g of v of x. This is dimensionless because we're dividing it by seconds per centimeter. So both of these curves are probability distribution functions. So they have the same area underneath. The area is 1. But at the higher temperature, it's shorter and wider. So the most probable velocity is 0. But, of course, that doesn't mean that nothing is moving. It just means half the molecules have a positive velocity and half the molecules have a negative velocity, and they cancel out to 0. So that's a normal Gaussian function. So the peak is always going to be at Vx is equal to 0, or Vy equal to 0, Vz equal to 0. So here's g of v, the speed function. Again, we're dividing by seconds per centimeter, so there's no units on the y-axis. So here, in this case, with low temperatures, you have the peak here. With higher temperature, you have the peak over here. So the top of the curve here, it's the most probable speed. So g of v dv is going to be equal to m times 3/2, or m over 2 pi kt to the 3/2 power, times e of minus mv squared over 2 kt. That's supposed to be k, that's Boltzmann's constant, obviously. Times 4 pi v squared dv. Now the 4 pi v squared dv term dominates at low speeds. So remember, lowercase m over k is equal to capital M over r, where m is the molar mass in kilograms per mole. So here's the question, what fraction are going a certain speed or higher? At increasing temperature, we're going to have an increasing fraction above a certain speed. So like, let's say we have at constant temperature, we have this g of function. We have argon, neon, helium. The molar mass of argon is 40. The molar mass of neon is 20. The molar mass of helium is 4. So as you can see, the lighter molecules are going faster. The heavier molecules are going slower. So again, what fraction are going above a certain speed? Higher mass means lower fraction. Now at low speeds, then the v squared dominates, but at high speeds, the exponent dominates. Now the average energy of translation, remember, is 3/2 kt. Notice there's no mass term, so that's not material specific. But energy of translation equals 1/2 mass times the average speed squared. That has mass, so it is material specific. And likewise, average speed squared is equal to 3 kt over m, or 3 rt over m. That is the end of chapter 15, section 4.